Hello everyone, I welcome you all to the next session. So these were the objectives of chapter 1, and today we will develop an understanding about the concept of continuum, and we will also gain some knowledge about the Newton's law of viscosity and Newtonian and non-Newtonian fluids. So first of all, the concept of continuum. So when we want to describe a matter, it is always assumed that it is continuous. Continuous means that there is no discontinuity in between the molecules, or there is no gap between the molecules in a matter. This can be highly true or it can be regarded correct for solids as well as liquids, because in case of solids the molecules are very closely packed to each other and there is no gap between the molecules in this case. Whereas in case of liquids, the molecules are also closely packed and the gap between the molecules in case of a liquids is also not substantial. So the concept of continuum or the continuity of a matter can be considered true for both solids as well as liquids. Why it is important? Since if we have to define a property, it can be any property, it can be your pressure, it can be your temperature, it can be any other property. So in order to define a property, we need some space coordinates, because the property is always defined in terms of a space coordinates or in terms of the time coordinates. Because as a specific example, if we take into a fluid into a consideration, when we talk about steady and unsteady flows, and when we talk about uniform and non-uniform flows, which we discussed in the previous video, so in that case the steady flow which has some relation with time will be called as a steady or unsteady flow, and the flow which has some relation with space coordinates will give you the uniform or non-uniform flow. So in order to define these flows or define these properties, it is always defined in terms of some space coordinates and time coordinates. So if we have to define these properties like pressure, temperature and other properties, so it is always assumed that the concept of continuum is valid. If there will be a gap between the molecules, the concept of continuum will not be valid, and we cannot define the properties as a function of time as well as space coordinates. So what we can say that for a solids and liquids, since they are very close, molecules are very closely packed to each other in case of solids and liquids, so we can say that the concept of continuum is valid in both the cases. And temperature or pressure can be a function of x, y, z and time coordinates t. But in case of gases, as we all know that the molecules are not closely packed to each other. So in case of gases, the concept of continuum will hold good or not is characterized by a constant number, because we don't know whether there will be the concept of continuum will be valid in case of gases or not, because the reason is that when you increase the temperature of the gas, the gap between the molecules will increase and the gases will try to expand. So we will not be in a position to tell whether the concept of continuum will be valid in case of gases or not. So we calculate a number called as a constant number. So if the constant number is less than 0.01, then we can say that the continuum of concept of continuum will be valid in that case. So what is constant number? It is basically the ratio of mean free path to the characteristic dimension. So mean free path, basically lambda by L, it is this ratio. So mean free path, as you all are aware of that, it is basically the average distance between between the two successive collisions. So we should calculate the mean free path first, and then we should be aware of a characteristic dimension. Suppose if it is a pipe flow, the characteristic dimension can be d. If it is a flow over a flat plate, the characteristic dimension will be L. So we need to find out the characteristic dimension. So if the constant number is less than 0.01, then we can say the concept of continuum is also valid in case of gases. As far as solids and liquids is concerned, the concept of continuum is valid. So in the nutshell, what is concept of continuum? The concept of continuum states that the matter is homogeneous and continuous. That is, there is no discontinuity. So the importance of concept of continuum is that, as I told you also, that if we have to define a property as a function of some space and time coordinates, the concept of quantum should be valid. So the concept of quantum is valid in case of solids and liquids, but in case of gases, under certain conditions, if the constant number is less than 0.01, the concept of quantum will be valid. The next important thing is the Newton's law of viscosity. So what is this Newton's law of viscosity? So for this, first of all, we'll take into consideration a one-dimensional parallel flow in which the velocity varies only in y direction, because we are taking into consideration a one-dimensional flow, and you know that the one-dimensional flow is a kind of a flow in which the velocity varies only in one direction. So in that case, the velocity is varying only in y direction or in the vertical direction. So as you know that the fluid flow always takes place in the form of layers. So here I have taken into consideration two layers, and the other layers, upper and the lower layer, are also shown over here. So I have taken a very small fluid element in which I can see there are two layers. So layer 1 and layer 2. So what will happen, as you know, whenever there will be a flow, whenever there will be a velocity, what will happen, there will be a wall on one side. Suppose we have a wall on the lower side, a surface on the lower side, or the flat plate flow is taking place. So what will happen? I will show you a condition in the next figure. Suppose we have this kind of a flat plate, fixed flat plate, which is fixed one. So what will happen over, we have taken into consideration a layer over from here, and this is the enlarged view over here. So what will happen? Here what we'll have, we will have a viscosity. More viscosity will be there. Here we have more viscosity, or we can say more resistance, to be more technically sound. Uh, we have a resistance over here, more resistance over here. Here the resistance is less. That's why the velocity is decreasing. Sorry, increasing, because the resistance is decreasing. So here the resistance will be more. So what will happen, the resistance is more over here, it will be transmitted to the other layer, it will be transmitted to the above layer, so on and so forth. So we are taking into consideration two layers. So the resistance over here is more, in between this is more, because it is being transmitted from lower part to the upper part. So this layer will upon the application of the velocity in this direction, this layer will tend to move towards that side, but this layer will try to resist it. So a field of shear stress will develop between the two layers, because it will try to move in that direction and it will try to retard, because Newton's law of third law of motion will come into action, because this layer is going towards the other side, but this layer will produce equal and opposite reaction, and this layer will tend to move towards that side. So since the force is a tangential, so a tangential stress or a shear stress will develop between the two layers on that particular area. So due to the parallel and opposite forces between two layers, a state of shear stress is developed. As I told you, Newton observed that this shear stress, the shear stress which is being developed between the two layers, is proportional to velocity gradient. If we take into consideration this figure, here you can see it is a fixed plate, and we have a moving plate. In between we have a fluid, and we are giving some force to it, we are trying to pull it, or we are giving some velocity to it. So this this plate is moving. So what will happen, a velocity profile like this will be there, and as I told you, a small portion of that is shown over here. So you can see this is the distance between the two plates, denoted by y. and it is a case of a one-dimensional flow because the velocity variation is only in one direction, that is in y direction. So here the velocity, local velocity will be 0, and here the velocity, local velocity will be equals to the velocity of the moving plate with which it is moving. So what will happen? So the Newton observed that the shear stress developed between the layers. There are different number of layers over here. So the shear stress developed between the layers is proportional to velocity gradient. Velocity gradient means the change in velocity divided by the vertical distance, the change in the distance. So we will take into consideration that the shear stress is directly proportional to velocity gradient. It was observed by Newton after some experimentation. So this tau is equals to mu du by dy, and you know that mu is what? It is a constant of proportionality. So this constant of proportionality is also known as the coefficient of viscosity, or simply we can also call it as dynamic viscosity. So as per the Newton's law of viscosity, shear stress is directly proportional to velocity gradient. Here I am talking about velocity gradient, and what we have considered it is a one-dimensional parallel flow in which the velocity varies only in one direction. So based on this, the shear stress is directly proportional to velocity gradient for a one-dimensional parallel flow. And we can write tau is equal to mu du by d by this formula. So the statement as per the Newton's law is that shear stress is directly proportional to velocity gradient. But if we remember the constitutive equation of the fluid, which we discussed in the very first lecture, in that case, the shear stress or stress basically was directly proportional to strain rate. In case of a solid, the stress was proportional to strain. And in case of a liquids, stress is directly proportional to strain rate because the continuous deformation of the fluid takes place. So stress is directly proportional to strain rate as per the constitutive equation of the fluid. So we can say that the general statement of Newton's law should be, as per the constitutive equation of the fluid, it should be shear stress is directly proportional to shear strain rate. But here we can see that shear stress is directly proportional to velocity gradient. So we know that this shear stress is directly proportional to velocity gradient for a special case wherein the case of one-dimensional flow has been taken into consideration. So it is only the special case of one-dimensional flow where u, local velocity of the fluid layer, is a function of y and the strain rate is equals to velocity gradient. So for a special case, strain rate becomes equal to velocity gradient when we take into consideration a case of a one-dimensional flow. So the general statement of Newton's law is that shear stress is directly proportional to shear strain rate. And for a special case of 1D flow, Newton's law is given by shear stress is directly proportional to velocity gradient, which we observed in the previous case. So as a whole, what we can say, if we have to define the Newton's law of viscosity, Newton's law of viscosity states, we can say that for the general statement of the Newton's law of viscosity is that the shear stress is directly proportional to shear strain rate, and for a special case of one-dimensional flow, shear stress is directly proportional to velocity gradient. So it is a specific statement, it is a general statement that should be kept in mind. Now coming towards the Newtonian and non-Newtonian fluids. So Newtonian fluids, as the name indicates, in that case the shear stress is directly linearly proportional to shear strain, and simply we can say the fluids which will observe the Newton's law of viscosity will be called as the Newtonian fluids. So non-Newtonian fluids, shear stress is not linearly proportional to shear strain rate, and shear stress is given by this formula wherein we have K as a consistency index and N is a flow behavior index. So those fluids which will not obey the Newton's law of viscosity will be called as the non-Newtonian fluids. We have different types of non-Newtonian fluids. Uh, as far as the Newtonian fluid is concerned, we have water as an example. There are other fluids which can exemplify the Newtonian fluids, but non-Newtonian fluids has different classifications. So in that category, we have the time-independent fluids, and under time-independent fluids, we have a pseudoplastic, dilatant fluids. So there will be dependence of time. With the passage of time, there will be change in the viscosity. So pseudoplastic fluids are also called as the shear thinning fluids, and n we call as the flow behavior index. In that case, in these cases, less than 1. So this n is always less than 1, so we can say it is a pseudoplastic fluid. Then we have a dilatant, where we call them as the shear thickening fluids, and in that case is greater than 1. So there are time dependent fluids, that there will be change in viscosity with respect to time. In the previous case, there is no dependence of time, there will be no change in the viscosity with respect to time. Basically there will be change in viscosity with respect to your applied shear stress. So in that case, viscosity increases with the increase in time, called as a thixotropic, and rheophatic fluids, where viscosity decreases with the increase in time. So we have these two categories: time independent fluids, non-Newtonian fluids, and time dependent non-Newtonian fluids. Quickly, I will talk about the examples of these. We have a pseudoplastic fluids. Different examples are there: ketchup, nail polish, and shampoo. Dilatant fluids are there: wet sand, suspension of starch. Then thixotropic, peanut butter, gelatin, gel, clay. So these are the examples of the thixotropic fluids. Rheophatic fluids have an example as printer ink, synovial fluids. So these are the examples of the rheophatic fluids. So why I'm not focusing on these I'm not explaining, I'm not going into the detail of these, because the scope of the fluid mechanics that we will discuss is only here in the Newtonian fluids. So we do not take into consideration the non-Newtonian fluids in this fluid mechanics. Otherwise, they are also of very important, great importance. But from the point of fluid mechanics, so we take into consideration only the Newtonian fluids. So non-Newtonian fluids we will not discuss and will not talk about in the coming chapters. So that's why I have given you the brief classification of these non-Newtonian fluids. So now coming towards a viscosity. Basically, from the Newton's law of viscosity, we have observed that there is some resistance which will be offered by the moving layers in due to the development of shear stress. So basically, what is viscosity? It is a property that characterizes the internal resistance being offered during the flow of a fluid. So remember, for viscosity to occur, there should be a fluid motion. When there will be no fluid motion, the layers will not slide, and when the layers will not slide, there will be no internal resistance, and when there will be no internal resistance, which means there is no viscosity. So viscosity occurs only when there is a fluid motion. So viscosity of a fluid can also be defined as it is a measure of its internal resistance to deformation. So generally it is denoted by mu, and its unit is Newton second per meter square, or we can also call it as a Pascal second. So it is also denoted by poise, and 1 poise is equals to 0.1 Pascal second. So this viscosity mu is also called as the dynamic viscosity or absolute viscosity. So whenever you will talk about dynamic viscosity or absolute viscosity, it is basically it will be noted by mu, and it is the resistance which will be offered during the fluid flow motion. So what is basically the cause of viscosity in case of liquids as well as in case of gases? In case of liquids, the viscosity is due to the cohesive forces. You know what is cohesion and adhesion. Cohesion means the force between the like molecules. So because the fluid molecules are very closely packed to each other, and the force of cohesion are dominant. So the force of cohesion uh, basically resist the fluid motion, or resist the motion of different layers of the fluid, so due to which resistance gets developed, and this resistance basically is viscosity of the fluid. So in case of a gases, because gases you know that they are not closely, molecules are not closely packed to each other. So in case of a gases, it is basically due to the molecular collision, the collision between the two molecules, between the different molecules, governs the viscosity in case of gases. So another term is there called as the kinematic viscosity. Basically, kinematic viscosity is nothing but it is the ratio of dynamic viscosity to the density of the fluid. So when you divide this mu by the density of the fluid, so it will give you the kinematic viscosity. So this, it is denoted by nu, and nu is equals to mu by rho. So nu is equals to mu by rho. It is the kinematic viscosity of the fluid. So unit, as you know, we can find out units from here when we divide Newton second per meter square divided by the density and units of density. So we'll get meter square per second. So the units of kinematic viscosity are meter square per second. So also we denote the density kinematic viscosity by stroke. So 1 stroke is equals to 10 raised to minus 4 meters square per second. So you can have a look into these two conversions from the book. You can see how 1 poise is equals to 0.1 Pascal second, and how 1 stroke is equals to 10 raised to minus 4 meters square per second. So whenever in a numerical or whenever in a problem the viscosity in stroke will be given, it means that it is the kinematic viscosity, and whenever the viscosity in poise is given, it certainly means that the viscosity is in it is a dynamic viscosity. So effect of viscosity, how the viscosity will increase or decrease, or how it will be affected by the increase of temperature. So viscosity of liquids basically generally decrease with the increase in temperature. You will feel that when you increase the temperature of a liquid, I'm talking about liquid, so the viscosity will decrease, the resistance which will be offered between the two layers will decrease, whereas in the case of gases, the decrease, there will be an increase in the viscosity with the increase in temperature. So liquids and gases have a different behavior. Viscosity will decrease in that case, it will increase in that case in case of a gases on the increase in the temperature. Why? The reason is that, as I have told you previously, in case of our liquids, viscosity is due to cohesive forces. The cohesive forces decreases on the increase in the temperature. So if the cohesion will decrease, the resistance will also decrease. So here in case of gases, the viscosity is due to molecular collision. So on the increase in the temperature, the molecular collisions will increase. So it will lead to an increase in the viscosity. So that's why viscosity increases with the increase in the temperature in case of gases, and viscosity decreases with the increase in temperature in case of liquids. Now, why it is very important, why we should understand the viscosity. So viscosity, since it is the resistance which is being offered between the two layers, so it is important. The reason being that the viscosity of a fluid can be related to the power requirements in two cases. Suppose we have to transfer a fluid from one location to another. If it will be more viscous fluid, you can appreciate that. If it will be more viscous fluid, what will happen? The more force will be required to transfer it from one point to another point. So viscosity directly can be related to the power requirement in this case, in the case of transfer of fluid from one point to another through a pipe or a duct. Whereas on the other hand, if you want to move a body through a fluid, if it is more viscous fluid, suppose a submarine is there, so a fish is there, if it is moving in a fluid, or aeroplane in an air, if it is moving through that medium, so it requires some energy, some power to overcome the resistance will be offered by the medium. It can be a gas or it can be a liquid. So more viscous fluid will be there. If you have oil, and if you have to move through the oil, you will require more power through that. If you have a water, you will require less power to move. And if you're moving in air, you know that it is again very less power is required to you. So if you want to move a body or through a fluid, so viscosity has an important role. More viscous the fluid will be, more power requirement will be there. So there are the two cases wherein viscosity of a fluid is very important, uh, and where it governs the power requirements in these cases. So next is compressibility and bulk modulus. Since we know that the fluids have a variable as well as the constant density, so on the application of pressure, there will be change in the volume, or it may be due to temperature also. So when we apply some pressure, there the volume will decrease. The volume of gas, or we can say of a liquid, will have a decrease. So we will take into consideration an example. Here you can see a piston cylinder arrangement which is showing the fluid compression. Here you can see the initial volume was V, and on the application of some pressure the volume has reduced by dV, and the net volume now is V minus dV. So on the application of pressure, or we can say on the increase in the pressure, the volume has decreased. So compressibility of a substance can be defined as the change in its volume on the application of pressure. Basically, compressibility is given by the compressibility coefficient, which is equals to minus 1 by V dV by dP. So this compressibility basically signifies the change in its volume on the application of pressure, or it may be due to temperature also. So upon heating and decreasing the pressure, the volume of fluid increases. Suppose if we are heating a fluid, the volume will decrease, or if we are decreasing the pressure or applying some pressure, the volume of the fluid will also increase, and vice versa is the case, which means that the fluid volume will decrease upon increasing the pressure and upon cooling the fluid medium. So quantitatively, compressibility is characterized by bulk modulus of elasticity. So bulk modulus of elasticity is nothing but it is the reciprocal of, or it is inverse of, compressibility coefficient, and it is a measure of compressive stress per unit volumetric strain. So if we write, it is noted by K, which is equals to 1 by beta C, and it will be given by this formula. So here you can see there is a negative sign in both the cases, and the negative sign indicates that there will be a decrease in volume with the increase in pressure. So if you're applying some pressure, if you're increasing some pressure, there will. So these were the books which were referred during the course of action. So I thank you very much for watching this video. So in this session we discussed about the concept of continuum, the Newton's law of viscosity, Newtonian and non-Newtonian fluids, and compressibility and bulk modulus. So in the next video we will talk about capillarity and surface tension, which are also an important aspect in fluid mechanics. So we will talk about these two terms in our next video. So till then I take your leave.